Ions are charged. Because of this charge, an electric field exists around the ion which spreads out evenly in all directions, getting weaker as it gets further away from the ion. When the field of a positive ion interacts with that of a negative ion, an electrostatic attraction occurs and they're drawn together. And this is the basis of an ionic bond. Because the electric field is all around the ion, it doesn't matter which direction another ion approaches from. Because of this, we say that the ionic bond is non-directional. It also means that if other ions approach the original ion, they can also be attracted to it, and new bonds can be formed, as long as the positive and negative ions are arranged alternately. As new ions add to the growing ionic structure, they do so in a very regular pattern. This allows them to be packed in as closely as possible, which makes the ionic bonds stronger. The result of this is that when an ionic substance is in its solid form, the ions are held in a regular, fixed 3D arrangement called a lattice. This is what happens when you grow a crystal of salt. Because different ions are different shapes and sizes, there isn't a single best way for all ions to pack into a lattice. Each ionic substance has a characteristic way of packing. As more and more ions are added to the lattice, the crystals eventually become macroscopic, and the shape of the crystal reflects the geometry in which the ions packed. For instance, sodium chloride packs into a lattice called simple cubic, and when you grow crystals of table salt, you'll see that the predominant shape is a cube. This animation from Vizchem illustrates how ions are packed in a sodium chloride crystal. Notice that although they're fixed in place in the lattice, they're still vibrating, which is a reflection of their kinetic energy. To melt the crystal, we heat it up. The hotter it gets, the more the ions vibrate, since the higher temperature means that they have more kinetic energy. Eventually, the kinetic energy of the ions overcomes the electrostatic attraction between them, and the ionic bonds are broken. The ions now move freely past each other, and the salt has become molten, or in its liquid state. In contrast to the cubic crystals of sodium chloride, the copper ions and sulfate ions in copper sulfate pack into an arrangement called triclinic, which doesn't have the right angles of a cube. This means the crystals characteristically grow into lopsided diamond shapes. Note that this is copper sulfate pentahydrate, which is the familiar blue form of the salt. This crystal actually includes water molecules among the ions. You can see in the formula that 5 water molecules are added. While the copper and sulfate ions are still locked in place by ionic bonds, the water molecules are held there by weaker intermolecular forces that you'll meet later. Incidentally, the study of crystals is called crystallography and played a vital part in much of 20th century chemistry and biology, including the discovery of the structure of DNA. So my task for you is a short research task. Borax is a pretty common chemical. It's used in cleaning products, and it's also used to make slime. I'd like you to look up the chemical formula and the proper name of borax. I'd like you to see if you can find out the name of the crystal type of borax. And then, if you were shown crystals of sodium chloride and borax, tell me, how could you tell which is which just by looking at them?